Good morning, students. So myself, Madhuri Mulik, working as a assistant professor in Electronics and Telecommunication Department, SIT Civil. So last session we have from the last session we have seen that the chapter number 2, that is MOSFET and its DC analysis. So in this chapter, so in the last session we have seen the MOSFET as the active resistor and current sink and source. So already we have covered the point, that is current, sink and source. So let us see the further part of the session. So we have seen the what is sub circuit, simple circuit and complex circuit. So this is our MOSFET biasing. So MOSFET as a diode and active resistor, already we have seen. So how it is implemented as floating resistor. Then last time we have started with the current sink and source. So in that, what is current sink we have seen. Then what are the two quantities characterized, that already we have seen, R out and V min. So now, so up to this means output resistance, by using the feedback we can improve, that we have seen. Then next point, so from this onwards we are going to continue this session. So increasing the output resistance of a simple MOS current sink. Okay, so increasing the output resistance. So small signal model for calculating the output resistance for the cascade current, which is shown in this figure. So what we are going to see, small signal model for calculating the output resistance for cascade current sink. Okay. So this is nothing but the equivalent circuit. So here transconductance into get to source voltage. Here the transconductance of the another MOS, uh, MOS. Then how we are going to increase that output resistance? Let us see. The loop equation is given by I out minus GM2 into VGS2 minus GMBS, that is biasing circuit, VBS into 2, VBS2 into RDS 2 plus I out into R. So taking the common things together and rearranging the equation becomes like this. But if you think for the VGS2 is equal to 0 minus Vs2, that is minus I out into R, and VBS2 is nothing but this. So therefore this equation V out, after the putting the values of this, the equation becomes like this, and from that again we have taken out that I out. So equation is like this. So R out is nothing but the V out divided by I out. So the value of the V out we have put here. Then I naught I out gets cancelled, and whatever the remaining, that we have written here. Okay. So if you think related to this term, they are approximately equal to the this term. Both sides they are negligible, and this is nothing but that the product of this transconductance and voltage. Then it is okay. Here is written that. Okay, so mu into 2 into R. So the general principle emerges. The output resistance of a cascade circuit is equal to R into common source voltage gain of, of the cascading resistance. Okay, so for this increasing the output resistance, cascader current sink is used, and from this we have concluded that this resistance is how many times increased, that is multiplication into the common source voltage gain of the cascading transistor. Then MOS cascade current sink we are going to see. So here M1 and M2 two transistors PMOS is used, P and NMOS is used, according to that we have implemented the equivalent circuit. So small signal output resistance. So noting that VGS1, okay, is equal to VG2 is equal to VB2, that is the biasing, is equal to 0. And writing a loop equation, we get the V out, that is V out is equal to I out minus GM2 PGS2 minus GMBS2 PBS2, okay, into RDS. That same thing we have repeated here earlier, that circuit arrangement of V out. So however VGS is equal to this, again we are going to put the values of this and taken common that the I out, and again writing that the R out, then I out gets cancelled, and whatever the remaining we have written here. So this second term again we have taken out, okay, because it is nothing but the higher value, then it is nothing but this. So what is the conclusion from this? So same as before, if R is equal to RDS 1, then bulk effect have little influence. Okay, when MOS cascade current is used, then bulk effect have little influence of that. Then let us see the next thing, that is current mirror. So what is current mirror? A current mirror replicates the input current of a current sink or current source as an output current. So the output current may be identical to the input current or can be a scaled version of it. Okay. So a current mirror replicates the input current of a current sink or current source as an output current. Okay. So the output current may be identical to the input current or can be scaled version of it. Okay. So what is mean by current mirror? Current mirror replicates the input current, okay, of current sink or current source as an output current. So the output current may be identical to the input current or can be scaled version of it. So let us see the current mirror. So here current source is and I out is taken. So the above current mirror are referred with respect to ground. Current mirror can also be referred with respect to VDD also and current inputs and outputs. So characterization of current mirror. A current mirror is basically nothing more than a current amplifier. Okay, what is meant by current mirror is basically nothing more than the current amplifier. So the ideal characteristics of the current amplifier are the output current linearly related to the input current. So we can say I out into current gain into I in. Okay, because current mirror is nothing but the current amplifier. So input resistance is 0 and output resistance is infinity. Also the characteristics, that is minimum voltage V mean applies not only to the output but also the input. Okay, so V mean input side is the range of V in over which the input resistance is not small, and V min out is the range of V out over which the output resistance is not large. So graphically, if you plot the current mirror, then input side and the output side. So input characteristics shows the slope where 1 upon R in gives the value, and the transfer characteristics is I out by I in, that the current gain if you calculate, and output characteristics is the in I out versus V out. So therefore, R out, R in, V mean out, V mean in, and AI will characterize the current mirror. Okay, so current mirror is nothing but the current amplifier. Okay, and I out is equal to AI into IN. So for that circuitry, input characteristics, transfer characteristics, and output characteristics we have seen here. Then if gate source matching principle is used, so show here, see here, gate and source, that the matching principle if we use, then if the gate source voltages of two or more transistors are equal and the transistors are matched and operating in the saturation region, then the current are related by the width by length ratio of the individual transistors. The gate source voltage may be directly connected or implied. Okay, so if we are using the gate source voltage of two or more transistors, gate source voltage, okay, two or more transistors are equal. How they are going to equal? Because the matched transistors are matched and operating in a saturation region also. So currents are related to the width by L ratio, individual of the transistor. So the gate source voltages may be directly connected to or implied. Okay, so that are given. This ID1 is given by constant, that W by L length into VGS1 minus PT1 bracket square. So the modified one equation becomes like this. Then for the ID2 current, again the same relationship we have written here, and for the modification. And if suppose these are the two transistors are matching, means what? VGS1 and VGS2 is matching, then this is nothing but the relation between that the two MOSFET, or we can say either one we can calculate. So the second thing is, if the drain currents of two or more transistors are equal and the transistors are matched and operating in a saturation region, okay, means these two currents are in this point these two voltages we have matched, in this we are going to match these two currents. So the transistor is, then the gate source voltage are related by the width by L ratio, ignoring the bulk effect. Okay, so this, for this reason, if the ID1 is equal to ID2, then VGS is given by this equation, or if W2 by W2 means width by length ratio of the two MOSFETs are equal, then VGS1 is equal to VGS, and VDS1 must equal to VDS2 for ideal result. Okay, so gate source matching either by the voltage of gate to source or either by the current. Then MOSFET current mirrors. So simple MOS current mirror is shown here. So they carefully see that the diagram. Two MOSFET are used and they are shorted at the gate, and they again connected to the drain of the first MOSFET. So assume that this VDS2 is greater than this VGS minus VT0. Then output current divided by input current is given by this equation. So if the transistors are matched, then that the constants are also matched and threshold voltages are also matched. So by assuming this, we can rewrite this equation and we will get this. So if VDS1 is equal to VDS2, then also this equation is like this. So therefore, the sources of error are VDS1 is not equal to this, and M1 and M2 are not matched. Okay, because each and every that the MOSFET having its own specification due to the fabrication process. Then influence of the channel modulation parameter lambda. So let us see, if the transistors are matched and the width by length ratios are equal, then I out by IN is given by this equation. Okay. So if the channel modulation parameter is the same for both transistors, its channel modulation parameter is the same for both transistors, then L1 is equal to L2. So note that one could use this effect to measure the lambda. Okay, so VDS1, VDS2, I1 and I0, and if you solve above equation for the channel modulation parameter, so you will get this ratio error into the 100% of that percentage we are going to calculate, and this is the VDS2 minus VDS. So you will get the various values of this lambda. Okay. Then, if influence of mismatched transistor. If suppose the transistors are not matched, then constants are also not matched, as well as that the threshold voltages are not matched. Therefore, if we have I0 divided by I1, the equation becomes like this. If the mismatched transistors are used. So how do you analyze the mismatch? So use plus and minus worst case approach and define that ratio, that equation once again. So like this. Okay. So substituting these terms into above equation gives these terms in above equations. So the equation becomes like this. Okay, and if we are finding out, so equation becomes like this. So taken out that the constant things outside and cancelling in a numerical and denominator. So assuming that the term added to or subtract from 1 are smaller than the unit equals. So this ratio is nearly equal to this value is okay. So the equation is nearly equal to 1 plus delta k dash divided by k minus 2 delta Vt divided by Vgs minus Vt. So also we can assume that this ratio is nothing but the plus minus 5%, and these values are plus minus 10%. So this equation is representing by that values, and we can calculate the error, that is plus minus 15% error if tolerance are correct, correlated to each other. Okay, so that is the influence of the mismatching of the transistor. Then illustration of the offset voltage error influence we are going to see. So assume that the threshold voltage is 0.7 volts and that the constant and the width by length ratio is like this. So if make the part of VGS causing the current flow, so V on more significant than VTN. So here VTN and ratio is also shown here for that the different values of the input current value. So is it clear that influence of that the error influence? Then influence of error in aspect ratio of the transistor. Okay, so W by L, that the aspect ratio. So aspect ratio of error in the current mirror. So see here shows the layout. Okay, so 1 to 4 current amplifier, 1 to 4 current amplifier. Assume that lengths are identical, L1 is equal to L2, and find the ratio error, that is this one, 5 plus minus 0.1 micrometer. The actual width of the two transistors are this one and this one. So if we are going to solve this, so we know that the tolerance is not multiplied by the nominal gain factor by 4. So the ratio of W2 and Wn are consequently the gain of the current amplifier. Okay, so this is given, and we have calculated that. So it comes 4 minus plus minus of 0.03. So where we have assumed that the variations would both have the same sign, variation. So it is seen that This ratio error is 0.75% of the desired current ratio or gain. Okay, so in this up to this influence of error aspects ratio of transistor, related to that the current mirror we have seen. So in this session we have seen the part of that the current sink and source, and the next point is current mirror. Up to this we have covered. Okay, thank you.